I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic on antenna arrays for the course Antennas and Wave Propagation. So, before going into the video consists of two sections. The first section we will discuss about the various types of array antennas and array antenna introduction. And in the second part, we will see about how to calculate total field of a two element array. So now coming to the array antenna definition, an antenna array is a system of similar antennas oriented similarly to get greater directivity in a desired direction. So the main aim of using antenna array is to increase the directivity so that we can get sharpest radiation pattern which is required. And it may be also defined as a radiating system consisting of several spaced and properly phased radiators or antennas. And the total field produced by an antenna array system is the vector sum of the fields produced by the individual antennas of the array system. An antenna array is said to be linear if the individual antennas of the array are equally spaced along a straight line. So, equally spaced antenna arrays are called as linear antenna arrays, and individual antennas in an antenna array system is termed as elements. So, the various forms of antenna arrays are given in picture. The two important categories of antenna is one is broadside array and another one is end-fire array. And according to the arrangement of the antenna, both the arrays are equal because both the antennas array systems consist of equally spaced antennas, so both are linear antennas. The difference is in phase of the array. So now we discuss one by one. The first category is broadside array. So the broadside array is one in which the number of identical parallel antennas are set up along a line and they are drawn perpendicular to their respective axis. And the individual antennas in broadside array are equally spaced along a line. So they are coming under the category of linear antennas. And each element is fed with current of equal magnitude and all the current are in same phase. And they radiates in broadside directions, that is perpendicular to the array axis, and the maximum radiation is relatively in with respect to the broadside directions and little radiation in other directions, and that is towards array axis. Radiation pattern of broadside array is bidirectional. And now coming to the end-fire array. End-fire array is the array which the individual antennas are fed out of phase, that is usually 180 degree. The end-fire array is one in which the number of identical elements are fed with current of equal magnitude, but their phase varies progressively along the line in such a way to make the entire arrangement unidirectional. And end-fire array may be defined as the arrangement in which principal direction radiation coincides with the direction of array. The end-fire array may be bidirectional, for example, two element array fed with equal current but 180 degree out of phase. So this diagram represents the radiation pattern of end-fire array. So by considering broadside array and end-fire array, both are linear arrays, but the difference is broadside array individual antennas are fed with current of equal magnitude and equal phase, but in end-fire array the currents are progressively varying and they are 180 degree out of phase. And with respect to radiation pattern, the maximum radiation of broadside array is in the direction perpendicular to the array axis, but in end-fire array the maximum radiation is towards the array axis. And the third category is collinear array. This is similar to broadside array, but the difference is in the arrangement of individual antennas in the array. So here the antennas are arranged coaxially, that is the antennas are mounted end to end in a single line. The individual elements are fed with equal in-phase current as in the case of broadside array. So, a collinear array can be termed as equal to broadside array where the direction of maximum radiation is perpendicular to the line of the antenna. Now, the activity. Next is the two element array. So, the two element array consists of 2 point sources with equal amplitude and phase, and this is the broadside case. Here, the total field pattern is the addition of patterns of individual sources. So, here the origin is at the center, antenna 1 and 2 are located at equal distance from the origin, and here the waves from antenna 1 reaches the distant point P later than the rays from antenna number 2 because of the path difference between the antennas 1 and 2, and it is denoted by 1 dash 2 dash in the diagram. And to calculate the fields at distant point P, we should at distance R from the origin O, and it is taken as the reference point for phase calculation. And now the path difference is calculated, and the path difference we have obtained as d cos theta meters. In terms of wavelength, it is d by lambda cos theta wavelengths, and phase angle psi is 2 pi into path difference, so it is 2 pi d by lambda cos theta, and this 2 pi by lambda is beta, so phase angle psi is beta d cos theta. Now, total field is E is equal to fields due to individual sources, E1 e power j theta 1 plus E2 e power j theta 2, and psi is the path difference. And now by calculating total fields by adding two individual antenna fields, it is given by E is equal to 2 E naught cos psi by 2, and substituting psi value as beta d cos theta, we get total field for two element array is 2 E naught cos beta d cos theta by 2. Now, taking the total amplitude E1 is equal to E2 is equal to E naught, we get 2j E naught sin psi by 2 for the 2 point sources having equal amplitude and opposite phase. So, because in equal amplitude and opposite phase, one field is opposite with respect to other, so it involves the negative sign for one antenna with respect to other antenna when the calculation of field. So the total field E becomes 2j E naught sin psi by 2 because sin formula involves minus in the middle, and so the total field is given by E is equal to 2j E naught sin beta d cos theta by 2. So now the assessment for long distance communication, which of the properties mainly necessary for the antenna, and it is high directivity, low directivity, low gain, broader beam width. The answer is high directivity. And which of the following is false about the single antenna for long distance communication is enlarging may create side lobes, no side lobes, high directivity is required, high gain is required. The answer is B, no side lobes. Thank you.